Welcome back to statistics. We've seen that there are two major kinds of studies in statistics: observational studies and experiments. Now we want to think a little bit about the kinds of conclusions that you can draw from these studies. It turns out that the kind of conclusion depends on where the data came from. Was it an observational study or was it an experiment? So let's take a look at a couple of slides here and then we'll look at some examples. We've already discussed the kinds of studies: observational studies in which data is collected all under the same conditions, and experiments in which data is collected from different groups of subjects under different conditions. Um, when we're thinking about drawing conclusions from studies, we need to think about where the data came from. We need to ask some basic questions. Can the results of the study be generalized to apply to a larger group? And if so, what group would that be? If the study is multivariate, does the study establish any associations or relationships between the variables in the study? And if relationships are present, can we assert that they are causal relationships? That is, relationships that come from a cause and effect kind of mechanism. So let's think about generalization first. A study is going to involve a certain number of subjects, and descriptive statistics will allow us to understand how variables behave among those subjects. But can we generalize that behavior and assert that it applies to a larger group? The answer is going to be yes, only if our subjects are representative of the larger group in question. That larger group is usually called the population. And so when we generalize, we have to establish that the subjects of the experiment or the observational study are representative of the population they were drawn from. The best way to obtain representative samples is to use what's called a random selection of the sample from the population of interest. Now, we'll talk a lot more about this. Sometimes that's easy to do, sometimes that's hard to do. But the essential idea is that in a random selection, each individual in the population has an equal chance of being included in the sample. And for that reason, there is no reason to expect that any one group would be overrepresented or underrepresented in the sample. And that would be a representative sample. How about finding relationships? Both observational studies and experiments can detect relationships between variables in a study. But relationships aren't always due to cause and effect. For instance, if I look at children's reading ability, I will find that it's correlated with children's shoe size. Children that wear larger shoes will tend to have more advanced reading abilities. Is that because big feet cause better reading abilities? Of course not. What's actually happening here is that as children age, their reading abilities get better and their shoe size gets larger. So this is an example of what statisticians call confounding. Sometimes a relationship can exist, but it's not really a cause and effect relationship because some other variable is affecting the characteristics that we're looking at. What we're really after in most studies is cause and effect relationships. And it's an unfortunate fact that observational studies can almost never establish firmly a cause and effect relationships. Only well-designed experiments can really establish these solidly. The downside, though, is that sometimes well-designed experiments are impossible to carry out, sometimes for practical reasons and sometimes for other reasons like moral or ethical reasons. So, how can experiments establish cause and effect? They do so by another application of randomness, namely the random assignment of subjects to treatment groups. What a random assignment of subjects to treatment groups does is it ensures that prior to applying the treatments, the experimental groups are the same on average. Because we've randomly assigned individuals to the various groups, there's no reason to expect systematic differences among the groups. Therefore, any significant differences in outcomes once the treatments are applied can't be due to any sort of pre-existing differences between the groups. They have to be due to the different treatments that were applied to the groups. And so this is the way that experiments can establish cause and effect relationships, whereas observational studies can't. And we'll have a lot more to say about this going forward, but that's sort of the basic idea. Actually, let me stop here for a second before we jump into independent and dependent variables and jump to the ebook to see if we can look at some examples about the concepts we've just discussed. What we're looking at here is section 2.1b, determine the conclusions that one can make from observational studies or experiments. So let's pop that open and look at the contents. Here, the key concepts, again, are going to be outlined for you in a little bit more detail than I just went through. In observational studies, we want to have samples that are representative so that we can generalize the conclusions, even if they're not cause and effect kind of conclusions. In an experiment, we can actually go deeper and uncover cause and effect relationships. And so then they give us some examples, and I'm going to go ahead and go through other examples in a second. But let me just point out some steps that they go through here in trying to determine the kinds of conclusions that you can draw from a study. They outline 4 steps. First, determine the kind of study. Is it an observational study or an experiment? Then ask yourself how random selection was being used. That's to determine if generalization is possible, and if it's an experiment, whether cause and effect can be determined. Identify the population from which the sample was selected, and then from all that, determine the conclusions. So let's take a look at some of their examples here and see how this plays out. I first want to look at an example of a survey that Rolling Stone magazine did about the preferences of their readers. So let's take a look. Rolling Stone sent out a survey to a random sample of 2,000 of its subscribers asking about their favorite band from the 1980s. When the result came back, U2 gets most of the votes, with 43% of those sampled voting for them. What conclusion can be drawn from this survey? So let's just take a look at how they go through that little checklist of steps to determine what's going on here. First, ask yourself, is this an observational study or an experiment? So Rolling Stone sent out a random survey to 2,000 of its readers and asked them about their favorite bands. There were no treatment groups or anything here, so this is an observational study, and that's right. How was random selection used? Well, they did say that they sent a survey to a random sample of 2,000 subscribers. So a random selection was made for the sample, and so that's going to mean that the results are generalizable. Third, identify the population from which the sample was selected. So Rolling Stone sent out the survey to 2,000 of its subscribers. So the population would be the set of all Rolling Stone subscribers. And that's right. And so finally, what can we conclude from this? Well, we have here an observational study in which Rolling Stone sent out a survey to a random sample of 2,000 of its subscribers. So the sample should be representative of the larger population of all Rolling Stone subscribers. Therefore, we should be able to conclude and generalize that the result that 43% of the respondents said U2 was their favorite 80s band, would be generalizable to the set of all Rolling Stone subscribers. And so if we look at their answer, that's right. Notice that what we're saying, what the survey result was that 43% was the 43% that preferred U2 was the largest group. Other bands may have been preferred, but none of them came in at 43%. They were all less than that. So when we generalize, we're basically saying that we expect that result to remain true among all Rolling Stone subscribers. The exact number among all Rolling Stone subscribers that prefer U2 might not be exactly 43%. In fact, we'd kind of be surprised if it were. But we would expect that that number would be somewhere near 43%. And we might also expect that other bands would similarly come in with lower a number of people who think they're the best. And so when we make that inference to the population of all Rolling Stone subscribers, we don't expect the fine details of the study to hold 100% true, but the overall conclusions we do. So that is an example of looking at a study and trying to determine the kinds of conclusions you can make from it. I'll go ahead and stop the video here. We'll pick up in our next one with a little bit more about studies, specifically about their independent and dependent variables and the idea of confounding variables. And until then, take care, and I will see you again soon.